Input analysis, it is important that you take several repeated measurements of your samples, either in the form of replicates or repeats, so that you are confident that the analysis was carried out correctly. This is to ensure that you obtain the best estimates of your samples that represent the properties of the population. In order to ensure that the value of your data is reliable, you need to perform statistical analysis. Currently, there are various statistical techniques available out there that allow us to calculate the reliability of the sample data from multiple measurements. Some of the popular statistical softwares include SPSS, you have Minitabs, or even GraphPad Prism. But if you're interested in performing multivariate analysis, you may want to go for Excel Stat or even SIMCA. It's important to make sure that your data is accurate and precise. Accuracy means how close a particular measure is to the true value. Example is this dartboard A. You can see that all the darts, which represent data points, hit the target, which represent true value. The darts are also close to one another. This indicates precision. So what is precision? Precision is a measure of how reproducible or how close replicate measurements become. If we look at dartboard B, you can see that although the darts are far apart from the target, they are all close to one another. So this indicates that the darts have low accuracy but high precision. So what do you think about dartboard C and D? Are they precise and accurate? There are a few basic measurements that are required for the report. First, we need to measure the mean of the data. Means will give you the best experimental estimates of the value that can be obtained from the measurement. It is an average value of all measurements. So once you have calculated mean value, we then need to calculate the standard deviation. Standard deviation is a precision indicator. It measures the spread of the experimental values and gives good indication of how close the values are to one another. Coefficient of variation, on the other hand, is a statistical measure of the relative dispersion of data points in a data series around the mean. What about standard error? What does it tell you? The standard error tells you how accurate the mean of any given sample from the population is likely to be compared to the true population mean. When the standard error increases, it means the data are more spread out. So here is just a summary of equations that we can use to calculate mean and also standard deviation. For mean is an average of all the measurements divided by the number of measurements. Standard deviation, on the other hand, is the square root of the sum of the individual sample minus by the true mean divided by the total population of samples. But if the number of samples is less than 30, you need to do square roots of the sum of the individual sample minus by the mean divided by the total population of samples minus 1. Here is how we can calculate the coefficient of variation. The coefficient of variation represents the ratio of the standard deviation to the mean. It is useful for comparing the degree of variation from one data series to another, even if the means are drastically different from one another. In food analysis, normally the data is acceptable if the CV is less than 5%. The lower the value, the better, as it indicates a high level of precision of reproducibility of the replicates. The standard error is calculated by dividing the standard deviation by the sample size square root. Sometimes, when performing analysis, it is possible that the data may be erroneous. There are many sources of errors. They can be personal errors, or we call it as blunders. Normally, the cause of blunders is due to carelessness. Personal errors are easy to identify. It can also be a random errors. Random errors will produce data that vary in a non-reproducible fashion from one measurement to the next. One way to identify random errors is by measuring standard deviation. Another possibility for the source of error is a systematic error. For systematic errors, the data produced are always consistently deviated from the true answer. For example, the measurements is always giving you 10% higher result. One way to overcome systematic errors is by recalibrating the instrument or equipment. In some analytical procedures, it requires us to prepare standard curves that are used to quantify some property of an unknown material. Good example for this is Lorry methods to measure protein concentration. So the technique itself is based on absorbance. Okay, so what happens is that the reagent will bind to the proteins and it will change into colored product. So the more intense the color of your sample is, the higher the concentration of the protein. But by just measuring intensity, it will not give you the actual concentration of protein. So what you can do is you can plot a graph of standard curve where you plot it again, the known concentration of your standards against its absorbance. Okay, so a series of calibrated experiments is carried out using samples with known property, and the standard curves is plotted from this data. Okay, so as I mentioned before about the protein, so you prepare a series of dilution of your standard. Standard is your protein here. Okay, your protein can be bovine serum albumin or even caseins, okay, with known concentration. So you have a series of different concentration of your standards, okay, and then you run the experiment. It will give you different intensity in terms of the color, and you take the reading, the absorbance reading, using UV-Vis microplate reader. So once you have your reading, absorbance reading ready, what you can do is you can extrapolate it into this graph, okay, where your protein concentration will be in the x-axis and the absorbance reading will be in the y-axis. Okay, from here, what you can do is you can find the best fit line that is drawn through the data, okay, using regression analysis. Here, the one I show you is a simple regression or linear regression model, okay, where the gradient of m, okay, and intercept at y, okay, which is the c. So the equation for linear regression is y equal to mx plus c. Okay, so once you have generated the equation, okay, you'll be able to calculate the concentration of protein of your unknown sample, okay, by measuring its absorbance. And here, because you want to find concentration, you can rearrange the equation to make it into x equal to y minus c divided by m. Okay, so what you want to find is x. But before you perform your calculation to find the concentration of your sample, you have to make sure that your graph has best fitted line. Okay, how well the straight line fits the experiment data is expressed by the correlation coefficient, or we call it R squared. The value of R squared can vary between 0 and 1, and the closer the value is to 1, the better the fit between the straight line is. So if you have experimental value of R squared equal to 1, this shows a perfect fit. Okay, here I have two different graphs, okay, graph A and B. Can you tell me which of these is a better graph? Okay, which one can we use to calculate the concentration of our unknown sample? Okay. Most modern calculation and spreadsheet programs have routines that can be used to automatically determine the regression coefficient, the slope and the intercept of a set of data. Again, the model that I show you here is the simplest model, which is linear regression. We can also use non-linear regression. At the end of the day, it depends on your data set, because what you want to get is the best fit line.